Hey everyone, we're diving back into the preprocessor. In the last lesson, we covered what it actually does while it's crunching through our code. One of those jobs is handling all the preprocessor directives, and that's exactly what we're tackling today. A preprocessor directive is basically a command for the preprocessor. It always starts with a hashtag followed by some keywords. In Visual Studio, as soon as you type one out, it usually turns gray. That's a nice little touch to help you spot them easily in your code. Now, the C++23 standard lists 16 directives. This means every compiler out there has to support them. Sure, some compilers throw in their own extra directives, but we're going to skip those. They're super specific, rarely used in day-to-day coding, and honestly, there are way too many of them. We're sticking to the essentials that work everywhere. We can break these directives down into a few groups. Conditional compilation. A big chunk of them is used to tell the preprocessor which parts of the code to keep and which to toss based on certain conditions. Macros and file includes. This is where you'll find your old friend include. Errors and warnings. Some directives are strictly for triggering errors or warnings during the build process. So let's kick things off with the one you already know. The most popular directive is #include. Its syntax is simple: a hashtag, include, a space, and the file name in either angle brackets or double quotes. We're currently in example 01.cpp. Usually this directive goes at the very top of the file. We use it all the time to bring in IO stream. What this directive actually does is grab all the text from the file you specify and just drops it right where the call is. It's a basic copy-paste job, nothing fancy. So why use it? First off, the C++ standard library is full of tools for your code. For example, IOStream has stdcout and stdcin. If we want to use them in this specific source file, we have to include that file. Now, you see that including in this context just means copying the file's content. I created my own file, myHeaderFile.h. You don't know what header files are yet. I'll explain that in a few lessons. But for now, just think of it as a file that holds some of my C++ code. In our case, it's just a regular global variable. I want to connect it to my .cpp file, so I write this code. The directive takes all the text in that file and swaps it into the call site. It's super simple, but there is a difference between the brackets and the quotes. If you use angle brackets, the preprocessor only looks for the file in the C++ standard library. So if I use angle brackets for my own file, I'll get a compiler error because my file isn't in the standard library, it's in my project. But if you use double quotes, the preprocessor looks in your project first. If it doesn't find it there, it starts looking in the standard library. This means we could technically include IOStream both ways. In the second case, the preprocessor would look through our project, find nothing, and then find it in the standard library. So here's the first tip. Use angle brackets when including standard library files and use double quotes when including files from your own project. You might notice that when I include my own file, I have to include the file extension, but I don't do that for IOStream. Why? It comes down to the history of C versus C++ and namespace standardization. In early versions of C++ pre-1998, library files looked like iostream.h, vector.h, and string.h. But when the ISO C++ standard came out in 1998, they made a major move. They ditched the .h, introduced the std namespace, and separated the C and C++ library headers. In C, all library files ended in .h, like stdio.h or math.h. C++ has equivalents: C, std, eio, cstring, cmath. In these files, all the tools were put into the std namespace and updated with overloads and templates. For example, you know the rand function that gives you a random number. That function lives in stdlib.h. If you type it and hit F12, it'll jump to the file where its prototype is. You can see the file name right here. You could include that file directly, but it's already inside iostream file. There's also cstdlib, where that function is wrapped in the std namespace, so you have two ways to call it. We'll break this down more when we get to the standard library and headers, coming soon. By the way, you don't strictly have to include header files. You can include files with any extension. Once we learn how to create headers, we'll be using this command all the time with all sorts of files. Moving on to the next one, the hashtag define directive. It has two main syntaxes. Hashtag define macro name expression and define macro name argument list expression. This directive creates macros. A macro is just an identifier linked to a specific expression. During compilation, that expression is simply swapped in wherever the macro name appears. Macros don't care about data type, scope, or C++ syntax. They work strictly at the text level, so the expression can literally be any gibberish you want to write. Let's look at the first syntax. Usually, macros are written in uppercase to make them stand out. You provide a name, then a space, then the expression, for example, the number 100. Now, everywhere you write that name in your code, the preprocessor will plug in 100. It's the most basic substitution possible. It's not a variable or a constant. We could create a macro for the math constant p. It's 3.1415, but the preprocessor just pastes this number into the code before C++ even starts checking for errors. Take a look at rand_max macro. If you hit F12 on it, you'll see its definition. Now you can actually read that code. The value on the right is just hexadecimal literal. In Visual Studio's dark theme, macros are usually purple, which makes them easy to spot. You might also see macros like underscore in underscore that have no expression at all. Is that allowed? Yep. In that case, the macro acts as a text label or a marker in the code. Most macros are holdovers from C. In modern C++, you're better off using global const expr data. A const expr constant is also evaluated at compile time, but unlike macro, it actually has a data type, which makes it much safer. Now for the second syntax, macros with arguments. These look a lot like functions. For example, I can create a macro that takes one argument and multiplies it by itself, even though it looks like a function call when you use it. Remember, it's just text replacement. If I pass the word number into that macro, the preprocessor just sticks number into the expression twice. But look what happens if I pass an expression like 2 plus 3. You'd expect 5 times 5 equals 25, right? Wrong. The preprocessor doesn't know math. It takes the literal string 2 plus 3 and plugs it in, resulting in 2 plus 3 times by 2 plus 3. The compiler then follows standard operator precedence. It does 3 times 2 first, so you get 2 plus 6 plus 3, which equals 11. That's why, when making function-like macros for math, you should always put parentheses around every argument in the expression to keep the math straight. The downsides are obvious: no type checking for parameters or return values. That's why modern C++ favors const expr functions. They also run at compile time, but have all the benefits of real types. We'll cover const expr in detail later. There are also variadic macros and __va_opt__ for handling multiple arguments, but you aren't ready for those yet. We'll save them for another lesson. If you need a macro with 2 or more arguments, just separate them with commas. Macros are used for plenty of things, like creating header guards, but generally the rule in modern C++ is don't use them if you don't have to. Use constants instead of simple macros, and use functions or templates instead of macro functions. Finally, we have the #undef directive, short for undefined. It's used to remove a macro's name from the scope. Imagine you include IOStream and want to name a variable randmax. You can't, because that macro name is now globally reserved. The preprocessor will try to replace your variable name with a number everywhere it sees it. To fix this, you can write #undef randmax. Now, every line of code below that forgets that macro exists and the name randmax becomes available for you to use. Another classic example. The windows.h file defines a macro called min. If you want to write your own function named min, it'll clash. You can just turn off the macro using #undef and then go ahead and define your function. Moving on to the next example and conditional compilation. There's a specific set of preprocessor directives that help decide which code actually gets compiled. Conditional compilation is basically a mechanism to include or exclude parts of the source text before the compiler even sees it. During the preprocessing stage, it can literally insert or delete chunks of code based on certain conditions. First off, why do we even need this? Imagine you're building a game that needs to run on different operating systems. Windows provides windows.h file, while Linux offers unistd.h. You have to use different tools depending on the platform, or maybe you're writing different code for x64 versus x32 architectures. To figure out which system we're targeting, we use macros combined with conditional compilation directives. Let's break them down. First, we have #if and #endif. After if, you write a condition that the preprocessor evaluates. If it's true, the preprocessor keeps that block of code. If not, it wipes that text from the file. To tell the preprocessor where that conditional block ends, you must write #endif. Think of it like a closing curly brace for the block. Without it, you'll get a compilation error. Here's an example. There's a built-in macro called _msvc_lang. It holds a value representing the C++ standard version of your project. This macro is baked into the compiler, so you won't find a definition for it. For instance, C++20 is represented by a specific long literal. The L at the end just means it's a long type. You can change the C++ standard in your project settings. If we set it to C++20 or higher, the condition is true and the code stays. If we drop the standard lower, the preprocessor deletes that code and trying to call a function from it will cause a compiler error. You might notice that in Visual Studio, this ignored code looks grayed out or transparent. That's a hint that the code isn't making it to the compiler. You can toggle this in Tools, Options, search for inactive code, and make sure the checkbox is ticked. Just like a regular if statement in your code, conditional compilation supports else if and else. The first condition starts with #if. Any following conditions used #elif. It's short for else if. If you want a fallback for when no conditions are met, use #else. Every block must end with #endif. It's pretty straightforward. Most programmers don't deal with this daily because it's mainly used when building libraries and tools that other developers use. But you'll definitely run into it when poking around library source code. Next up, sometimes you just need to check if a macro exists at all. For example, Visual Studio has two main build modes, debug and release. Debug is for development. It helps you find bugs and understand the code. Release is for the final product. It optimizes the code for speed. In debug mode, the compiler creates a macro called _debug and sets it to 1. We can check for its existence using #ifdef. short for if defined. If the macro exists, the condition is true. If we switch to release mode, that macro disappears, and the preprocessor will strip that code out. There's also hashtag if endif, if not defined, which checks if a macro doesn't exist. For example, the macro win32 indicates you're on Windows. If I'm on Windows 11, that macro exists. I could write code that says if we are not on Windows, compile this specific block. That code would compile on macOS or Linux, but not on my machine. Finally, C++23 added hashtag elifdef and elif endif. These are just shortcuts for else if defined and else if not defined. They're just combinations of hashtag elif with the definition checks, so they don't really need a separate explanation. Moving on to the next example. Imagine we're writing code that relies on tools from the C++17 standard. If a programmer tries to compile it using an older standard, like C++14, we want to throw an error directly in the compiler to let them know. We can use the hashtag error directive for this. You just write your error message to the right of the directive. I've already set this project to C++14, so you can see the error popping up right now. If we try to build the project, it'll fail, and that exact text will show up in the error list. Once we switch the project settings back to C++17, the error vanishes, and we can compile without a hitch. Essentially, hashtag error forces a compilation failure with a custom message. Now, if we completely removed the conditional compilation and just left the C++17 code in a C++14 project, we'd still get compiler errors. However, those errors might be super confusing. Things like file not found or unknown identifier. We'd waste a lot of time trying to figure out why files are missing or why things aren't defined, when the real issue is just the C++ standard setting. There's also the hashtag warning directive, which was officially added in the C++23 standard. Instead of killing the compilation, it just throws a warning. It lets the process finish, but gives the programmer a heads up that something might be off. Alright, let's wrap this up with the last few directives. The first one is going to feel a bit weird. It's the hashtag line directive. It lets you manually override the values of the built-in macros underscore underscore line underscore underscore, that means line number, and underscore underscore file double underscore, means file name. We'll dive into those macros in the next lesson, but to put it simply, you see those line numbers on the left side of your editor, right? When the compiler hits this directive, it starts counting lines from whatever numbers you give it, and it swaps the file name in the error logs to whatever you specify. There are two ways to use it. You either just provide a number to change the current line count, or a number plus a new file name. Here's a practical example. Imagine you're working with code that was generated by another program, like a parser. If there is a bug in that generated code, the compiler would usually point you to a line in a massive, messy temporary file that's a nightmare to read. By using hashtag line, the generator can point back to the original source file where you actually made the mistake. So instead of saying an error in main CPP or example.cpp at line 10, the compiler tells you the error is in some source.meta at line 44. It saves you a ton of time. Where do you actually see this in the wild? First, parser generators like Yawk, Lex, Bison, or Flex. They turn grammar rules into complex C++ code. Hashtag line helps you see errors in your grammar file rather than in the code soup the tool generated. Second, embedded SQL like pro**C or SQLJ. When you write SQL queries inside C++, tools convert them into API calls. The directive links runtime errors back to your original source files. Third, shaders like GLSL or HLSL. Shader tools often combine multiple files into one big buffer before sending it to the GPU. Hashtag line is inserted at the start of each chunk to make debugging possible. Fourth, template engines. Any system that builds C++ code based on metadata or other languages uses this. Next up is hashtag pragma. This one is special because the C++ standard doesn't actually force it to do anything specific. It's basically a way for compiler developers to offer extra features that aren't in the official standard. The rule is, if a compiler sees a hashtag pragma, it tries to interpret it. If it doesn't recognize it, it must just ignore it and move on like nothing happened. In short, the C++ creators gave compiler devs a hook to add their own custom commands. These vary depending on which compiler you're using. Since I'm using Visual Studio, the MSVC compiler, I have access to a ton of them. You can Google MSVC pragma to see the full list on Microsoft's site. Here are a few common ones. Hashtag pragma once. It's a modern way to handle include gars, so a file doesn't get included twice. Almost all compilers support this now. Then hashtag pragma pack. Controls memory alignment for structures by removing extra padding bytes. Very common in MSVC, GCC, and CLang. Hashtag pragma warning. Lets you surgically turn specific warnings on or off in your code. The syntax is different for every compiler. Hashtag pragma message. Drops a message into the compilation log. It's like hashtag warning, but it just shows up in your output window as info. C++ 11 also introduced the _pragma text operator. It does the exact same thing as hashtag pragma, but you can use it inside macros. Why does it matter? Because you can't stick a standard hashtag pragma inside a hashtag define. The preprocessor can't handle a hashtag inside a hashtag. _pragma fixes that limitation. Finally, there's the null directive, which is just a single hashtag on the line by itself. It does absolutely nothing. You'll occasionally see it used to visually clean up complex macro chains or in very niche scenarios. For our purposes, just know it's a do-nothing command. Finally, we have two distinct directives that also start with a hashtag but work quite differently from the classic ones. These are specific MSVC compiler extensions used for hooking up external binary modules. First, there's the hashtag import directive, which is used for working with COM, component object model components. When the preprocessor hits this, it takes a specified file like .dll, .tlb, or .exe, reads its type library and automatically generates C++ header files like .tlh and .tli for you. The point of this is to save you from having to manually describe complex COM object interfaces. Then there's the hashtag using directive. This is used to import metadata in C++, CLI, managed C++ projects. Think of it as a bridge between the standard C++ world and the .NET world, like C# or Visual Basic .NET. Just to be clear, this isn't the standard C++ we're currently studying. It basically replaces hashtag include for compiled .NET assemblies. Instead of reading a text-based header file, the compiler reads the metadata directly from the binary. That's it for this lesson. Thanks for watching. If you enjoyed the video, you can support me by liking it, leaving a comment, subscribing to the channel if you haven't already, donating through the link in the description, or using the YouTube Thanks feature. If you want to reinforce what you learned in this lesson, you can become a channel member and get access to all the practice lessons. Just find the practice video with the same number and work through the tasks together with me. See you in the next lesson. Goodbye.